Hello and welcome everybody to the first lecture on autonomous navigation for flying robots. My name is Jürgen Sturm and I'm a postdoctoral researcher in the computer vision group at the Technical University of Munich. This course is about quadrotors, and I guess that most of you will already have seen a quadrotor in action. Maybe some of you even own a quadrotor or have flown with one yourself. This one here is a very popular platform. It's called the Parrot AR drone. It was originally meant to be a children's toy, but it turned out that this is a very versatile platform also for quadrotor research and teaching with quadrotors. To pilot it around, originally the idea was to connect to it with a smartphone, and then the quadrotor will copy the motions of the phone. So if you tilt your phone forward, it will move forward. If you tilt it backwards, it will tilt backwards and then also fly backwards. Same for left and right. The thing that makes it so cool for us is that it has a whole bunch of integrated sensors, and that it transmits all of the sensor data back over the wireless so that we can use it then on the computer. For example, it contains accelerometers and gyroscopes that it uses to estimate its attitude and to keep the quadrotor leveled. It also has an ultrasound sensor to measure the distance to the floor and then to keep the height, the flying height of the quadrotor constant. It also has a visual odometry sensor that estimates the horizontal speed of the quadrocopter. That's, for example, important during hovering or during flying in general. And it also has a forward camera at a higher resolution that you can use to shoot images or shoot nice aerial videos. And with that, you can, for example, fly around your house, look around a corner, or if you fly high above your house, you can record nice aerial videos of it. And as nice as it is to pilot a quadrocopter by yourself, the question that comes immediately into your mind as a computer scientist is how can you actually make this quadrotor fly autonomously? And this is actually the main goal of this course, to teach you how to program the quadrocopter so that it becomes autonomous. And that involves, of course, all kinds of topics. For example, we have to estimate the internal state of the quadrotor from its sensor readings. That means we need to know its attitude, but we also want to know its position, and we estimate that from GPS, noisy GPS readings, for example, or images that we're getting from the quadrotor. And once we have the state, the next question then is how can we generate suitable control commands to make the quadrocopter fly towards the desired goal position. And then also to generate a whole path, collision-free path that takes the quadrotor from A to B. So this is the course content by week, and this week we start with an introduction showing why a quadrotor flies, what the flight principle is, what sensors it typically carries on, and then we will briefly review current state-of-the-art methods in quadrotor research. So with that you'll get a good feeling for what's currently out there and what the open problems are. Then in the second week we will give you a brief recap on linear algebra and look in particular then at 2D geometry and coordinate transforms between different coordinate systems. In the third week we will then extend this to 3D geometry. In particular we will look at projections of cameras using the pinhole model, and we will introduce the mathematical models for all kinds of sensors that are typically employed on a quadrotor. In the fourth week we will then look at motors and motor controllers in particular, and this will then give us the possibility to steer the quadrotor in simulation towards the desired goal location. In week 5 we then introduce probabilistic state estimation. We will do that first by giving a brief recap on probability theory, and then we will look at Bayes' law and how that can be used to infer the world state. In week 6 we extend this then to the so-called filters, like the Bayes filter, but of course also the Kalman filter, and then in the exercises you will implement parts of a Kalman filter, of an extended Kalman filter, to track the position of a quadrotor given GPS signals. Then in week 7 we will introduce so-called visual odometry sensors, and we will look in more detail how these sensors work and what the underlying algorithms are for computing visual odometry quickly. And I'm really looking then forward to week 8, where we will present you some really cutting-edge research results from our group here, just to show you what we are currently working on and present some of the really new approaches that we've been publishing over the past years. This course, as I said, consists of 8 weeks. Every week there will be video lectures, roughly between 30 and 45 minutes long. These videos will be interleaved by interactive exercises. This will be interactive quizzes, where you have to type in the solution, and also arithmetic problems where you'll have to do some calculations on paper. But actually the most interesting part are the hands-on programming exercises that you will have to do in Python. We have developed a web-based simulator for a quadrotor, and this means that you can immediately try out all your skills that you have learned during this course on a simulated quadrotor. And we took special care that actually the code that you will be writing will be also executable on a Parrot AR drone. So if you happen to have a Parrot AR drone, you can try out the solutions to the exercises directly on the real thing. This was now the first video. In the next video, I will introduce why quadrotors are so cool and what the potential applications, also commercially relevant applications of quadrotors might be in the future.